I'm back at it again with some math things. This time, I'll be using a platform called HIA to give you a short and simple, and probably poor, explanation of Q-learning, which I think is a fascinating and useful tool. After I created a script and slides, the HIA platform allowed me to create this. The animations of the virtual character, or me, and the audio here was created completely automatically. I'll break this presentation up into a few parts, and I'll try to keep this self-contained. I'll assume that you have a basic knowledge of neural networks and artificial intelligence. Let's get into it. First, let's briefly talk about what Q-learning is. Q-learning is a type of reinforcement learning. Reinforcement learning, in turn, is a class of methods for creating AI when you don't know the optimal outputs for a given input and want to create an AI that does. Reinforcement learning methods use stimuli like rewards and punishments in order to get the model to learn the optimal policy, which are the best actions in each state. There are multiple subclasses within reinforcement learning, like genetic algorithms, which are the same way in which organisms evolve, or Q-learning, which is what we will talk about here. Next, let's talk about how Q-learning works. For this explanation, let's imagine we are trying to train an agent in a grid world to find its way to a destination. The basis of Q-learning is a Q-table, a table in multiple dimensions with axes of each possible state, in this case position, and each possible action, in this case, movements in each direction. In each cell of the table is a Q-value, a measure of how good each possible state action pair is, or how good it is to take a given action in a given state. If we have a full and accurate, or full enough for our purposes, Q-table, in each situation we can select the action with the highest Q-value, and that would be the optimal action. In the beginning though, we of course don't know the Q-values for each pair, and how do we figure them out? Let's imagine our agent in this grid world, and I'll show how it can be trained. The first step is pretty simple, you can just find the agent's state in the Q-table, not counting actions yet. The second step is a bit more interesting. When using the Q-table in practice, it could seem logical to pick the best action all the time, but in training the agent needs to explore and try new things. There are a few ways to introduce some exploration, and I have two here. Epsilon greedy exploration, epsilon being a constant between 0 and 1 determining how much the agent explores, attributes a 1 minus epsilon chance to picking the best action, and an epsilon chance to picking a random action. This lets it both explore new things and take the best path. Softmax exploration attributes a probability towards picking each action depending on the Q-value of the action. I'll give you a second to look at the softmax equation on screen. The third step is interesting too. After an action is taken, a Q-learning agent can receive a reward or punishment, some examples being perhaps a penalty for moving too much, which would penalize being inefficient, or a reward for getting closer to the objective, motivating the agent to reach the objective. Both rewards and punishments can be of different scales, too. How the state changes can depend on what the actions do, but also things like the obstacle states which, in our grid world example, are states where moving through them won't do anything. In this step, you see what would happen if the agent were to take the chosen action, including if it would receive a reward or punishment, and importantly how strong that feedback is, and how your state would change. In the fourth step, you change the Q-value of your state action pair using something called the Bellman equation. It takes in the current Q-value of the state action pair, the reward, and the best, or highest Q-valued, action in the state that the taken action would bring the agent to. It also uses a learning rate and a discount factor, which determine how much it changes the Q-value each iteration and how much it considers the possible future rewards when changing the value of the current state, respectively. In a given state with a given action, you plug everything into the equation, then update the state action pair of the state that you took the action in, accordingly. I'll give you a second to take a short look at the Bellman equation. In step 5, once you've updated the Q-value, you move the agent on according to the action chosen, then you go back to step 1 and do it all again. You can let the agent keep exploring and learning in this loop until the policy, or the best action in each situation, converges to something good enough and stops changing. As it runs, you can also change hyperparameters like the learning rate or the constant that is in your action picking function, letting you change how it learns over time. Throughout this, I've said a few times that once the Q-table is built up, the agent should just keep following the same, optimal actions and not touch the Q-table, but this isn't actually a good thing to do. Even when running in practice, the agent should continue updating its Q-value estimates, for two reasons. Firstly, this can allow the agent to keep refining its Q-table and therefore keep finding better and better policies. It's hard to know when training is complete, especially in more complex situations, so letting the agent keep improving is very important. Secondly, as you have learned so far, Q-learning essentially functions in practice by figuring out how good each state is to be in, then choosing correct actions using that information. But the problem is that, of course, how good each state is to be in depends entirely upon the environment. This means that small changes to the environment can throw the agent off a lot. If the agent just keeps following its original Q table, never changing it, it can make completely incorrect decisions because the Q table wouldn't adjust to the new environment it finds itself in. But, allowing it to continue exploring and training in practice also means that the model can adapt and learn the correct Q values again for different situations. This allows the model to learn like we do, for example, changing and adapting its knowledge dynamically based on new, unexpected situations. I won't be going into much detail about this at all, but neural networks can also be implemented with Q-learning, creating something called deep Q-learning. It is a powerful reinforcement learning strategy that can help mitigate some of the limitations of traditional Q-learning that we will discuss now. Given that the backbone of Q-learning is the Q table, which must be filled with correct Q values, which naturally requires trying out many actions in many different states, situations with very large state or action spaces can take a very long time to train. Q-learning also is difficult to apply to continuous state or action spaces, which many real-world things are, given that it relies on the Q table, which is by nature discrete. It's important to note that there are some strategies that can allow it to work on continuous state spaces, but, to be honest, if you wanted to use reinforcement learning in a continuous space, there are better alternatives, like PPO, meaning Proximal Policy Optimization. Deep Q-learning can help mitigate the problem of training in large state spaces by interpolating between states and actions, and in general using the good qualities of neural networks to further improve the already powerful technology of Q-learning. It alone, though, cannot solve the difficulty in applying Q-learning to continuous state and action spaces, given that deep Q-learning still relies on encoding the Q table. In conclusion, Q-learning is a powerful reinforcement learning method, and it has many capabilities. I hope you learned something from this introduction to Q-learning and enjoyed seeing this. Thank you.